Hello everyone, welcome to the first session. In this session, I would like to discuss differential equations. As we all know, mathematical physics is one of the most important paper that we can expect in these examinations such as CSIR NET or JEST or something like that. So let us jump into differential equation. So basically, differential equation is very useful while solving mathematical problems involving physics. For example, if we discuss about Newton's laws, we are very familiar with Newton's 3 laws of motion. Of these, the second law is called the law of that involves the physical interpretation of force or even the mathematical expression of force in terms of a differential equation. So if we write force as dp by dt, which is indeed a differential or the time derivative of linear momentum, which is termed as force. It can again be simplified as mass into d square x by dt square. So in these equations, you may encounter the expression such as d by dt or d square by dt square, etc. These are derivatives with respect to time. This is actually the first order time derivative of momentum, and this is actually the second order time derivative of position. So basically, differential equations are those equations which involve these kind of derivatives. So in physics, we will encounter such equations a lot. For example, this is a good example of force. If we move on to some harmonic oscillator, there also we will find differential equations. So in physics, we will encounter lots of applications of these differential equations. So let us jump into differential equations. Now, if we want to solve differential equation, first we have to identify the type of differential equation. Before jumping into the types of differential equations, let us find or let us discuss two parameters or two definitions, that is order and degree of a differential equation. So let us discuss about the order and degree of a differential equation. So basically, what do you mean by order or what do you mean by degree is that if we consider a differential equation which has this derivative terms, for example, if I am considering a differential equation d square x by dt square plus omega square x is equal to 0. This is a very famous differential equation. In this equation, if we check the differential term, we will get d square x by dt square. So order is nothing but the order of the derivative term or the order of the highest order derivative term. So for example, for another example, if we find the differential equation d square x by dt square plus d raised to 4 by dt raised to 4 plus dx by dt plus x is equal to 0, this is also a differential equation. Here we can find that the highest order is d raised to 4, dx raised to 4 by dt raised to 4, d raised to 4x by dt raised to 4. In this equation, we can find that the highest order term is dx raised to 4 by dt raised to 4, d raised to 4x by dt raised to 4. This is a fourth order term. So order is nothing but the highest order of the derivative term. So we can finally say that order is nothing but the highest, that is simply the order of the highest order derivative term. This order stands for the order of the differential equation we are considering. So I think you all get the idea. Now let us move on to degree. degree. You may be confused with these two terms, but remember, order always stands for the highest order derivative term in the differential equation. The order of the highest order derivative term in the differential equation is the order of the differential equation itself. Okay. Now, degree. Degree is nothing but the power of this particular term. Which term? The highest order derivative term. For example, if I have a differential equation d square x by dt square plus dx by dt the whole square plus x is equal to 0. Please remember that d square x by dt square is not equal to dx by dt. D square x by dt square is the second order derivative of x with respect to time, where dx by dt the whole square is the square of the first order derivative of x with respect to time. So simply the degree of this particular differential equation is 1. Why? Just because the highest order derivative term has the power 1. So in this particular example, we can say that the order is equal to 2 and degree equal to 1. This is very important to identify the order and degree of the particular differential equation we want to solve. I think everyone got my point. Okay. Being enlightened by the two terms order and degree, now we can move on to the classification of differential equations. Basically, we classify differential equations according to their order. So, we will discuss about differential equations of different orders. In our syllabus for NET or GATE or JES, we are only limiting ourselves to the first two types of or first two degrees of differential equations, that is the first order differential equation and second order differential equation. Of this, we now discuss first order differential equations. So let us jump onto first order differential equations. So basically, what do you mean by a first order differential equation is that it involves the term, the first order derivative term of the variable. It can either be d by dx or d by dt or d by dy, depending upon what is our main variable and what is our independent variable. There may be two variables, there is an independent variable and there is a dependent variable. We are taking the first order derivative of the dependent variable with respect to the independent variable. That is, we are doing in this session. So depending upon the type of variable or the which variable we are taking according to our convenience and our problem, we are classifying our differential equations. So let us jump on to the classification. The first type is called variable separable. The first type in first order differential equation is variable separable. So variable separable is a type of first order differential equation that itself speaks the property, that is, we can separate the variables. So if we have a differential equation of the form f of y dy is equal to say phi of x dx, then this kind of variable, this kind of equations are coming under the heading of variable separable. So I would like to frame this class in such a way that I will discuss the type of the differential equation, how it can be identified, then what are the steps to be taken to solve this problem. This is my formalism to solve differential equation. So you can copy it if you find it convenient. So this is the form of the differential equation that is termed under variable separable. Okay. Now to solve this differential equation or this type of differential equation, what are the steps to be taken? Let us discuss. The first step, step 1. Step 1. Separate the variable. The equation may not be given like this. Okay, the given equation may not be seems like this, that is, it may not be separated in either side of the equal to sign. So we have to separate the variables. So the first step is that separate the variable to get this form, that is f of y dy equal to phi of x dx. This is our first step. Then what will be our second step? Obviously we can find that in this expression, in either side of the equal to sign, we have explicit functions of each kind. For example, in this particular case, the left hand side will give the explicit function of y only and right hand side will give the explicit function of x only. So it is quite simple to solve this equation. So in step number 2, we will integrate both sides. So simply we will do integral f of y dy equal to integral phi of x dx. Keep in mind that in left hand side we are integrating in terms of y and in right hand side we are integrating in terms of x. So you can add in this step itself you can add a constant of integration too. So simply this step involves integration in either side of the equal to sign and the addition of this integration constant. This is all about variable separable. I think you all got the idea. Okay. Now let us discuss a problem involving this kind of differential equation. So let me write the question first. The first question is that solve the differential equation, solve the differential equation x raised to 4 dy by dx plus x cube y minus equal to minus sec xy. See, this doesn't look like anything we have studied yet, but don't worry, we can solve this. Expect these kind of problems should be that can be asked in the coming examination. Now let us discuss this particular example. At first glance we may see that this equation does not look like anything we have studied yet, but don't worry, we can make it ourselves into that way that we already studied. Note the point that we cannot separate this particular equation with this term involved, that is xy, which is included within the sec. We know that this is an angle, so we cannot split this up. So we have to do a substitution instead. Then only we can convert this particular equation into variable separable form. Let us give a substitution. So before jumping into that, let us rearrange this equation as x cube into, we can take x cube outside this two terms. So x cube into x dy by dx plus y equal to minus sec xy. Okay, now let us substitute xy equal to v, a new variable. Put xy equal to v. So then what will be dy by dx? So dy by dx can be solved as, we have to apply product rule in this term, that is first function x into dy by dx plus y into dx by dx is 1. Y is equal to dv by dx. Is that clear? We can substitute this expression here. So what will be the final result? That is x cube into, we can substitute dv by dx instead of this term. So x cube into dv by dx is equal to minus sec xy is nothing but v. This is our final substitution. So now how we can convert this into our desired form? This is itself separable because we can rewrite it as dv by sec v is equal to minus dx by x cube, isn't it? So now we can simply integrate this we know that 1 by sec v is nothing but cos v. So cos v dv equal to minus dx by x cube. We can integrate on both sides and give a constant of integration. We know that cos v is nothing but, integral cos v is nothing but sin v equal to minus integral 1 by x cube dx is nothing but 1 by 2x square plus c. So finally we can rewrite it as, substituting back, we can rewrite it as sin v is nothing but sin xy equal to 1 by 2x square plus c. This will be the solution of the differential equation given. See, this is quite simple, but keep in mind that we can only solve a differential equation if we can convert it into the general form that we are familiar with. Okay, I hope you all get this problem. So now we can move on to the next type. So for the second type, we will call it as homogeneous differential equation. So we were discussing about the first order differential equations, and the second type among the first order is homogeneous differential equation. This homogeneous will come in the second order also, but it is quite different compared to this. So basically, what do you mean by first order homogeneous differential equation is that first we will write the form. If a differential equation can be expressed in the form dy by dx is equal to f of xy by g of xy, provided the degree of these two functions f and g should be same. Keep in mind that degree of f and g should be same. Then only we can say that this is a homogeneous differential equation. For example, if we encounter a problem such that dy by dx is equal to x cube by xy, is that a homogeneous differential equation? No. Why? Because in the numerator term the total degree is 3, but in the denominator x will have a degree 1 and y will have a degree 1, so in total it will have a degree 2. So this will not be a homogeneous differential equation. I think you got my point. So now how to solve this differential equation? So we are writing the steps to solve this kind of differential equation. First we should put a substitution, that is y is equal to vx. Now if we know y is equal to vx, then dy by dx is equal to, where x and y, v is also a function of x, so we have to apply product rule here also. So we can write it as v plus x into dv by dx. Substitute this value instead of dy by dx in the above equation, differential equation, then that equation will become a variable separable. So in step 2, substitute this equation, say this is equation 2 and our homogeneous equation will be, one second, our homogeneous equation, this will be equation 1. Then we can say that substituting the equation 2 in equation 1 will give a variable separable. So in step 2 substitute this equation in equation 1. In step 3 make the equation variable separable, or separate the variables, then it is just like the variable separable, that is step 4 integrate and constant of integration, and keep in mind that we substituted our y to v, so we have to substitute back our y. So substitute back y is equal to Vx, or nothing but v is equal to y by x. Then we will get our final equation. If you have any confusion, we can clarify it in our example. So let us write an example. So for homogeneous, let me write the example of a homogeneous differential equation. Question: solve the following differential equation. Solve the following differential equation: 2xy plus x square y dash equal to 3y square plus 2xy. This y dash is nothing but the first order derivative of y with respect to x. Since x and y are the variables, we can clearly say that y dash is nothing but dy by dx. Y double dash is nothing but d square y by dx square. This dash means we are taking derivatives with respect to our independent variable. So now let us solve this. Before jumping into the solution, keep in mind that we have to check for the homogeneity of this kind of equations. So for checking homogeneity, we should write it in our standard form, that is dy by dx is equal to, if x and y are the variables, then dy by dx is equal to f of xy by g of xy. Can we write it in this form? Let's try. That is 2xy plus x square, y dash is nothing but dy by dx equals 3y square plus 2xy. Keep this dy by dx in left hand side and just take this term to the right hand side. So we will get dy by dx is equal to 3y square plus 2xy divided by 2xy plus x square. Now checking the order and degree. So in this particular case, the order is 1, and degree we should check for individual terms. This is having degree 2, this is having combined degree 2, this is having also combined degree 2, and this is having combined degree 2. So all these terms are of degree 2. So this entire equation will have, entire polynomial is having degree 2, and this denominator is also having degree 2. Keep in mind that during product it gets add up, and during sum the degree remains same. That's the basic principle. So this is of course a homogeneous differential equation. Now let's try to solve this homogeneous equation. In order to solve this differential equation, we have to substitute y is equal to vx and dy by dx is equal to v plus, first derivative v plus x into dv by dx. Okay. Now substituting this here, we will get in the left hand side v plus x into dv by dx, that is v plus x into dv by dx is equal to, now substituting for y square, we will get 3x square v square plus 2x square v divided by 2x square v plus x square. So taking x square common and cancelling out, we will get 3v square plus 2v divided by 2v plus 1. So further taking v out of this, we will get 3, now I think we don't need to simplify further, we just want to take variables separated, that is x into dv by dx is equal to 3v square plus 2v by 2v plus 1 minus v, which is equal to, we will get 3v square plus 2v divided by 2v square plus v. which is equal to 3v square plus 2v minus 2v square minus v divided by 2v plus 1, which is equal to v square plus v divided by 2v plus 1. Now separating the variables, we will get, taking this term to the left hand side and x terms to the right hand side, we will get 2v plus 1 by v square plus v is equal to 1 by x dx. Integrating here dv, we will get, this is actually v square by v, its derivative is in the numerator, so we can apply the logarithmic result. So we will get log of v square plus v is equal to log x plus, I am taking this integral or this constant, say this is c dash, and I am substituting this for log c. Since c dash is a constant, so log c is also a constant. So we can rearrange this, we can take this to the left hand side and this will become log a minus log b, that is equal to log a by b. So we will get, and taking anti-logarithm, we will get v square plus v equal to xc. We can either take this x to the left hand side, or we can use the log ab property here, so we can get xc. Substituting back v square is equal to, or v is equal to y by x, we will get y square by x square plus y by x is equal to xc. So taking LCM, we will get x cube, so we will get the final result as y square plus xy is equal to xcx cube. So this will be our final result. I hope everybody get the point to solve how we can solve the homogeneous type of first order differential equation. Now for the third type, I would like to call it as linear differential equation. So this is the third type of first order differential equation of the form, linear differential equation will be of the form dy by dx plus p into y equal to q, where p and q are explicit functions of x only. Functions of x only. Keep in mind that p and q does not contain any terms of y. So this is the form of first order linear differential equation. Now for the solution, we have to apply different steps. Step number 1, we have to find the integrating factor. We have to find integrating factor. I can represent it as IF. If we write our differential equation in this form, that is our standard form, then integration factor can be calculated as IF is equal to e raised to integral p dx. Keep in mind that we shall not apply the constant of integration for calculating integrating factor. We need not apply integrating factor. Oh, I'm sorry, we should not give constant of integration in this particular integration. Now if we got this integrating factor, then the solution, that is step number 2, we can solve this linear differential equation by y into integrating factor is equal to integral of integrating factor into q dx, where q is the function of x only, which is in the right hand side of our standard differential equation. This is our final solution of linear differential equation. I hope you all got my point. Now let us discuss an example. So for this example, I would like to write question, that is solve the differential equation, this is a bit lengthy, x cube minus x into dy by dx minus 3x square minus 1 into y equal to x raised to 5 minus 2x cube plus x. First of all, we have to arrange this equation to our standard form. In this particular case, if we check for homogeneity, we already know that in this term, this is actually having the degree 3 and this is 1. This is having degree 2 and this is having degree 0. So we cannot use the homogeneity type. We cannot use homogeneous type of differential equation for solution. So we have to check whether this come under the title of linear differential equation. So arranging this to our standard form, we will get dy by, we can take this coefficient and divide it throughout this equation. So we will get dy by dx minus, we can divide this 3x square minus 1 by x cube minus x into y equals x raised to 5 minus 2x cube plus x divided by x cube minus x. Now we can say that this is our dy by dx and this is our function with respect to x. This is an explicit function of x which can be termed as p, and this is an explicit function of x which can be termed as q. So this is simply our standard form of linear differential equation. Now we can try to solve this. First of all, let us try to rearrange the RHS, the right hand side of this equation. So we can rearrange this by taking x common in numerator and denominator. We will get x raised to 4 minus 2x square plus 1 divided by x square minus 1, taking x in numerator and denominator and cancelling out each other. This is nothing but x square minus 1 the whole square. You can check it. X square the whole square, that is x raised to 4 minus 2 into x square into 1, that is 2x square plus 1. So this can be represented as this. Cancelling out each terms, we will get x square minus 1 as the simplification of right hand side. I think everybody got the step. So now we can rewrite our original differential equation as dy by dx minus 3x square minus 1 by x cube minus x is equal to x square minus 1. Now we can find the integrating factor. Integrating factor is nothing but e raised to integral p dx, which is equal to e raised to integral 3x square minus 1 by x cube minus x dx. Checking this equation, we can see that the denominator term can take derivative. This can be simply simplified as this is nothing but the derivative of this term. So we can apply the logarithmic result, that is e raised to integral log x cube minus x, which is equal to, this is actually a minus here because p is nothing but minus of this term. Okay, so we have to apply the minus, and this minus will make this a fraction, that is 1 by x cube minus x. So this is the integrating factor. Now for the final solution, we know that the final solution is given by, the final solution is y into integrating factor is equal to integral of integrating factor into q dx, that is y into 1 by x cube minus x is equal to integral 1 by x cube minus x into, what is q? Nothing but x square minus 1 dx. So here again we can take x common, and in right hand side we will get, if we take x common, we will get x square minus 1 numerator and denominator, so it got cancelled, so we will get 1 by x dx. So finally we can write it as y into 1 by x cube minus x is equal to log x plus c. So this is the final result. We can rearrange it further as y is equal to x cube minus x into log x plus c into x cube minus x. This is the final solution of the given problem. I hope everybody got my point. So this is the way we will solve linear first order differential equations. The fourth type of first order differential equation is actually a special case of linear differential equation. It is termed as Bernoulli's differential equation, or it is also known as reducible to linear differential equation. This is actually a non-linear first order differential equation, but we can reduce it into linear differential equation by a substitution. So generally Bernoulli's equation will be of the form dy by dx plus p into y. Up to this it is exactly equal to the linear differential equation, but in right hand side we will get a function of y as y raised to n, where n is the power of that y term. In this case we have to substitute, we have to give a substitution as z is equal to 1 by y raised to n minus 1. Therefore dz by dx will be given by 1 minus n into dy by 1 minus n divided by y raised to n into dy by dx. Now substituting this to our differential equation, we will get, that is, we are just substituting this result to our equation, and instead of dy by dx we will substitute this term. So finally we can rewrite it as 1 by y raised to n dy by dx plus 1 by y raised to n minus 1 p equals q. Now further simplifying it and substituting the result of z here, we will get 1 by n minus 1, 1 by 1 minus n into dz by dx plus pz equal to q. Now we can further simplify it as, since 1 minus n is just a number, we can take this to the numerator. So we will get dz by dx is equal to 1 minus n into pz, plus 1 minus n into pz equal to q into 1 minus. Now this equation becomes a linear differential equation, and we can find the integrating factor and substitute. In the final step we can substitute back the value of z to y, and we will get our final result. This is the special case that can be reduced to linear form. I just mention it. If you want, you can write down this. So for the final case in the first order category, we have to discuss about exact differential equations. Exact differential equation. So as usual we have to write the form of our differential equation first. So this will be just like m of xy into dx plus n of xy into dy equal to 0. This will be the form of exact differential equation. Now there is a condition to check the exactness of the differential equation. So the condition is given by the partial derivative of m with respect to y should be equal to the partial derivative of n with respect to x. If this is satisfied, then this equation can be called an exact differential equation. Now for the solution, we can find the solution. Step number 1. In the first step, we have to integrate m with respect to x by keeping y constant. In step number 2, we have to integrate n, but keep in mind that this n should not contain any term which is having x, that is except terms with x. Integrate n with respect to y. Clear? So you should exclude any term with x in n. Now combine these two. Step 3, add these two, and this will give a constant. Or in other words, in one step I can write it as solution is given by integral m dx keeping y constant plus integral n except x terms dy equal to constant. This is the simple step to find the solution of an exact differential equation. Let us check a differential equation of this kind and find the solution of that differential equation. So the question is given by solve the differential equation 5x raised to 4 plus 3x square y square minus 2xy cube into dx plus 2x square y minus 3x square y square minus 5 y raised to 4 dy equal to 0. So we can have this as our m and this as our n. If we try to find dou m by dou, so before that you can just check for homogeneity. This is actually a homogeneous equation too, but instead of homogeneity I would like to solve this as an exact solution if this satisfies the exact condition. So keep in mind that a differential equation can at the same time be a variable separable, be a homogeneous, be an exact, and so on and so on. The thing is that which is the easiest way or which is the way we know to solve. You should use that way to solve the differential equation. I am taking this as an example, that's why I am trying to solve this equation. So dou m by dou y will be given as, this will become 0, this will become 6x square y minus this will become 6xy square, and dou n by dou x will be given as, this will become 6x, sorry, I think there is a mistake, this is x cube, sorry, this is x cube, 6x square y minus this will give 6xy square. So these are exactly the equal terms, so we will get this differential equation as an exact differential equation. Now for the solution, we know that we just want to integrate m in terms of dx plus integrate n without x into dy equal to a constant. So integrating m, what do you mean by m? M is nothing but 5x raised to 4 plus 3x square y square minus 2xy cube dx plus integral. Without x term there is only one term, that is minus 5 y raised to 4 dy equal to constant. So integrating this with respect to x, we will get 5x raised to 4 will give 5x raised to 5 by 5, that is x raised to 5 plus this will get x cube y square minus 2, sorry, 2 got cancelled, x square y cube minus this will be given as y raised to 5 equal to a constant, that is c. This will be the solution of our differential equation. So I think you all got my point. So we have to discuss more problems. I think we can discuss it after discussing the second order differential equations too. So as a nutshell, we can say that we try to identify what is meant by differential equation, what is the order and degree of a differential equation, then the types of differential equation, especially first order and second order, and the types of first order differential equations. They include, the first one is variable separable, then homogeneous, then linear, then Bernoulli, and finally exact differential equation. There are other types of differential equations there, but for net or gate or just, we only want to study about these kind of differential equations, first order differential equations. So in the next class, we will discuss about the second order differential equations. So stay tuned. Goodbye. Thank you.